In this lecture, we're talking about the ocean physics behind net zero, and I'd like to start off with a question, which probably not something you've thought about very much, but why is the deep ocean cold? You probably think you know the answer to this question. You think, well, it must be cold because the sun can't get down there. All the heat from the sun is absorbed in the top few millimeters, in fact, of the ocean, and the mixing by the wind only takes it down the top few tens of meters. But if you think about it, that only explains why the deep ocean isn't warming up. But why is it cold in the first place? And it really is very cold. If we look at a section through the Atlantic, so this is a sort of south to north section in the Atlantic, you can see that over most of the depth, so it's about, on average, about 4 kilometers deep. So this is, remember, this has been exaggerated by about a factor of 1,000 in the vertical. If I showed you this to scale, it would just be a straight line on the screen. I tried to do that, but it was rather disappointing. This scale is 12,000 kilometers. So if we look in the tropical Atlantic, around here, over a few hundred meters, you go from surface temperatures, getting on for 30 degrees, bath temperature almost. You go a few hundred meters down, and you reach temperatures that you'd have to travel thousands and thousands of kilometers north to find them. So we have this massive contrast in the rate at which temperatures change in the vertical and how they change in the horizontal. And it's even more extreme in the Pacific. Most of the Pacific is almost at freezing temperature. You can see it's all this purple color. That's down near 0 degrees. And, you know, in this, some parts of the tropical Pacific, you actually, if you were in scuba diving depth, so in the sort of depth you can get to with just a sort of regular air tank, you could actually die of hypothermia before you're, not that this is recommended, before you die the bends, so to speak. So because the temperature contrasts are so great in the vertical. So be careful when you're scuba diving off Hawaii. So why is this? By the way, just getting back to this profile, you know, you might think, well, it's cold because it can't be heated up. Well, that's a sort of very, you know, if you don't mind me saying so, that's a bit of an Aristotelian way of thinking. Aristotle was convinced that everything had a sort of natural state. Aristotle was a Greek philosopher, scientist. Much of science, people call philosophy lots of, you know, footnotes to Plato. Science is largely tidying up Aristotle's mistakes. So one of Aristotle's big mistakes was he thought everything had a natural state. So the natural state of a cart was stationary, or the natural state of any object was stationary, and you had to keep pushing it to keep it going. Which meant, of course, Aristotle could never understand how the planets moved, because he couldn't work out what pushed them. Of course, Galileo, quite a few years later, worked out that actually the natural state of something was just to keep going in whatever it was doing. And the same, you know, unless there's something to slow it down. And the same goes for temperature. The natural state of water is not cold. If it's insulated, the natural state of water is just to stay whatever temperature it's at. So why is it at this temperature in the first place? And, I mean, by the way, water conducts heat, as you know. I mean, if you've ever got soaked from the rain, you'll feel that. It's actually one of the best conductors of heat that's not a metal that's out there. And so if you hold a nail in a gas flame, again, not recommended, but you'll notice the temperature equilibrates, you know, evens up along the nail quite quickly. Within a minute or two, temperature will be uniform along the nail. Water, I said it was one of the best conductors of heat, but it's not nearly as good as any metal. So if you take a glass of water, just say 10 centimeters deep, or better still, a styrofoam cup, so you don't need to worry about heat going down through the walls of the container, it actually would take several hours for you to warm it up by conduction from the surface. So that's the contrast between, you know, a metal object like a nail and liquid water, even though water does conduct heat. But if you, by the way, the depth which temperatures penetrate by conduction, the length of time it takes for a warming at the surface to penetrate down by conduction goes with the square on the depth. And that's sort of, again, okay, before you sort of start, he's moving into maths, I'm going to tune out at this point. That should be fairly obvious to you anyway, because what's driving heat along the nail or down through the glass of water is the gradient, is how fast the temperature is changing, either in the vertical in the glass of water or along the nail. And the further you go, the less the average temperature contrast per unit length, the less rapidly temperatures change, so the slower it moves heat along. So you can do the sum in your head if you want. If I tell you that it takes several hours for a glass of water, 10 centimeters or styrofoam cup of water to equilibrate temperature, it would take several thousand years for conduction to get down through, even just several hundred meters of water. So then you might, wait a minute, several thousand years ago, 20,000 years ago, the Earth was in an ice age. Maybe this is because of the ice age. Okay, it's not, okay? Because, of course, if you go that route, you might think, maybe sea level rise is all recovery from the last ice age. And then in the last lecture, I commented on the number of people who like to write me angry emails telling me that they've discovered that climate change is entirely natural. So, no, that's not the reason that deep oceans are cold. Because even back in the ice age, surface temperatures in the tropics were only a few degrees colder than they are now. Certainly not that kind of temperature contrast. So, the oceans have been around for billions of years. I'm hoping by now you should be a little bit puzzled. Why is the deep ocean so cold? Because even just conduction would warm it up. And the answer is a very sort of important one, and a very important one for our net zero story. I hope you've all, I'm sure you're all aware that temperature is not the only factor that affects the density of seawater. Any idea where this is? The sort of hint is, I guess, also in the newspaper. That's the Dead Sea. This is somebody doing the classic thing of reading a newspaper in the Dead Sea. If you have enough salt in water, it's very dense, and as another much better scientist than Aristotle, as Archimedes point out, that means that you can float in it at high enough that you can actually read a newspaper. So the salt content of water increases its density, as well as, if you want to increase the density of water, so these lines show you contours of density. It gets more dense in this direction. You can either cool the water or you can make it saltier. So both of these things make seawater denser. So cooling, for example, the wind blowing over the surface of the ocean, cooling it down, that helps make water denser. But evaporation and the formation of ice, that also makes water saltier. When ice forms, the salt is left behind. So if you're ever stuck on an ice floe, lots of survival tips in this lecture. Eat the ice, don't drink the seawater. Yep, because it's much fresher. But what happens is, as seawater freezes, the water that's left behind it becomes saltier and therefore denser. So there you are. Here's water getting, as you reduce the temperature and increase the salt content, the water gets denser. And so the places where water can escape to the ocean depths are places where it's very dense at the surface to start with. And those are places where it's very cold and where the formation of ice and the action of wind blowing over the ocean act to make water particularly dense. So places like this, that's an ice floe in the background to give you a hint about where you are. You've got the wind, a storm in the North Atlantic, causing lots of evaporation, lots of spray. The water that's left behind is getting saltier. Ice is forming. That's also making the water saltier. Eventually, that surface water becomes denser than the water beneath it and slides away down into the ocean depths. Now, crucially, once the water's left the surface, there's nothing down there to warm it up again. There's no equivalent to rain formation or sun in the atmosphere to warm up different. It's on its own. There's nothing happening down there. So once it's gone, ocean water remembers the temperature and the salt content it had when it was last at the surface until it gets back to the surface again, which may be many, many hundreds of years. So water forms in these isolated regions. So here they are. There's a few regions, the Labrador Sea, the extreme North Atlantic, and this region near Antarctica, where the water's cold enough to escape down into the ocean depths. So all of the water that you see in 90% of the world's oceans has got there through these so-called deep water formation regions. So it really is Arctic temperatures below the tropical Pacific. Just a few, 50 to 100 meters down, you find Arctic temperatures because it's Arctic water. It's come from the Arctic. Because once it's down there, it can't mix with the water above it because it's so cold and dense, and the water above it is being heated by the sun and made less dense as a result and sits on top. So here's an amazing graphic, courtesy of NASA, which shows you this circulation. Do you see the water flowing up through the North Atlantic and reaching this black region? The color indicates the density. And in this region where surface density is at its highest, the water drops away down into the ocean depths, and then it can't mix with the water above it anymore because it's so dense. It's stuck down there, and it travels southwards, on average, back through all these sea mountains, remembering this is massively exaggerated in the verticals, so it's not nearly that spiky in reality. And you can see that this downward, undersurface, deep flow coming back down through past the tropical Atlantic, no mixing with the surface because you've got this density contrast, the lighter, less dense water above, more dense water below, and goes all the way around the world, back out into the Pacific, and then eventually, somewhere else in the oceans, it resurfaces again. It's a fantastic graphic. The only thing I don't like about it is that it sort of implies, you see here, the water's sort of popping up at one place. And that's actually very misleading. That's not the way the ocean works. There's these few places where deep water is formed, but there's no such thing as a shallow water formation region. It's actually much more like an aquarium pump, but working in reverse. So if you've got a tropical aquarium, you've got to have this sort of pump thing that sort of circulates the water, pulls water from the bottom, and pushes it out at the top. And so over the rest of the aquarium, you've got a very, very gradual downwelling of water, and then you've got this one little pipe pumping it back up to the surface. So, the oceans work in exactly the same way in reverse. You've got this sort of few points where you've effectively got a pipe from the surface down to the deep ocean, and then over the rest of the ocean, it's slowly upwelling. Yep. So that's the only criticism I've got of this otherwise fantastic animation from NASA. Anyway, I think that's what's really interesting about just the way the ocean works, but what has it got to do with net zero? Well, it helps us understand where energy goes in the climate system. Now, remember from the previous lecture, and we had a sort of 10-minute recap before this lecture started for those who weren't there, we emphasized that our climate system is fundamentally governed by this flow of energy in from the sun and the flow of energy back out into space, a little bit like a bathtub. If you crank up the tap and increase the flow of energy in, if this is a sort of the plug hole of the bath, then the heat content of the climate system increases until the pressure driving energy out balances the pressure of the energy coming in. And we sort of demonstrated that with our gadget, which we'll come to in a minute. So where we are now is we're adding energy to the climate system because of the increase in greenhouse gases over the past century and a half or so, at about 2.5 watts per square meter added up over the whole Earth's surface. That adds up to a lot of energy. And because the world's already warmed up, about 1 3/4 is going back out into space, and the difference between those two numbers is 3/4. The maths in this lecture is all really straightforward. And so the world is warming up by that much energy per, that's per square meter of the Earth's surface we're seeing. But that doesn't tell you itself how fast the temperatures are going up. I'm telling you how fast the energy content of the climate system is going up, but what does that mean for surface warming? And to understand that, you need to understand where the energy is going, how it's distributed around the climate system. So this is a graph of where energy has gone in the climate system since 1960. There's a 1960 here to the present, or 2018 or so. And this shows you how heat energy has accumulated in the climate system. And one of the sort of most impressive things about this figure is this fine red line you see here, which shows when we use satellites to work out how much energy is being taken up by the climate system as a whole every year, and then compare that to where, measuring the oceans and the land and the ice caps, where energy's gone, we get a very good match. Do you see how this red line matches the blue line very well? So we know where the energy's going in the climate system, which, you think, well, how hard was that? Really hard. Okay, lots of people had to do a lot of work to do that, but it's done, and it's lots of things like this, because of course what we're doing here in order to work out what the energy content, this is the pale blue here, is the top 300 meters of the oceans. The slightly darker blue is the top 700 meters, and then darker still. This is the top 300 meters above the green line. This is the top 700, and so on. So you can see how these different regions are giving you different, how the energy is distributed through the ocean system. And as a result of that, you see that in order to be able to observe that, we've had to instrument up the Earth's oceans with vast numbers of drifting buoys to work out how fast temperatures are going up in different regions. But this has been done, and there's a lot of uncertainty sort of pre-1980s, because we didn't have these buoy networks back then, but we've got it pretty well wired up now, so we know where the energy's going. And this is what's accumulating in the climate system. The unit here is something called a zettajoule. And you've probably heard of a joule of energy. That's the energy it takes to warm up a liter of water by 1 degree. I think I've got that right, or a kilogram of water by 1 degree. So a zettajoule is 1 followed by 21 zeros, joules. So it's a billion trillion joules. So quite a substantial number. If you want to compare that to, so that's the 0.75 watts per meter squared we talked about. If you want to compare that to a number you might be more familiar with, that's the total amount of energy we generate, mostly from burning fossil fuels, but from hydropower and everything else in the world over the same period. So the actual amount of energy we generate, and by the way, 75% of that is wasted as well, so the actual energy we use would be quite a small fraction of that. Okay? So that's whole of humanity compared to the energy that's accumulating in the climate system as a result of past emissions of greenhouse gases. So people often ask me, does it matter that a power station is generating heat itself, or that the steam coming out of the cooling towers of a power station is quite hot? It is hot. It's steam. Is that what's causing global warming? No, because that energy is tiny compared to the energy that's being trapped by those greenhouse gases that that power station might have produced. That's the big impact on energy in our climate system, not the energy we actually generate from burning stuff. Okay, by the way, notice here there are some extra stripes down here. That little beige one is energy accumulating on land and energy accumulating in ice, mostly by melting ice, is the sort of grey one. And finally, the purple one is the tiny amount of energy that's accumulating in the atmosphere. And the reason that's quite small compared to the ocean is that the atmosphere has a very low heat capacity compared to the ocean. It's much easier to warm, it doesn't take nearly as much energy to warm air up as it takes to warm water up. And the land one is quite small because the land, only the soil really warms up, the sort of top few. You're not, whereas in the oceans, you're warming up kilometers of water. So why is the energy being distributed the way it is? Just to point out to you, most of it is in the top 700 meters. More than half is confined to that top 700 meters of water. A lot of it's in the top 300 meters. And the rest, most of the rest is going down into the ocean depths. So why is this? You can sort of see what's happening here. These are temperature trends in the global oceans. And you can see here in the Pacific in particular, all the warming's happening at the surface. Really nothing happening further down. In the Atlantic, it is penetrating down, but only in a few regions. That region of the North Atlantic, that region of the Southern Ocean, okay? Those same regions that we've said we've seen water penetrating down into the ocean depths, because those are the regions where the surface is connected to the deep ocean. And we get this siphoning off of surface waters, and as the surface warms, you get a siphoning off of surface heat. So that's where the energy penetrates down into the ocean depths. So this is what takes us back to our climate model, our Gresham climate model, which I will wake up, I hope. And just to remind you, so fluid flowing in represents energy coming in from the sun. I explained in the last lecture that if I was to make this to scale, because the energy flowing in from the sun is so enormous compared to the changes due to greenhouse gases, we need to have it sort of 100 meters high, and Gresham couldn't quite afford that. So this is scaled down, the natural flow flowing in from the sun and flowing back out into space. Okay? Space is downwards. Okay? Again, Gresham couldn't afford a sort of anti-gravity arrangement, but you can see the basic idea that we have a balance between energy flowing in from the sun and energy flowing back out into space. If we crank it up if we increase the speed of the pump, we see the level of water in this tube rises, pushing fluid out into space, energy back out into space. That corresponds to temperature, the surface temperature, and it rapidly reaches a new equilibrium level. And if I increase the speed by the same amount again, it goes up by about the same amount again. All right? So far, so good. So far, so simple and relatively obvious. This would be the way the climate would behave if the whole world were kind of like the Pacific, and you just had a sort of surface of water completely isolated from the water underneath. But it isn't. And this is why we need to think about the way the oceans behave, the way the deep oceans behave, in order to understand how the climate responds. So as I promised in the last lecture, this is the bit where we uncork the ocean. I'll switch this off before I do that. And now I'm going to drain this quickly. Sadly, there isn't a tap at the bottom of the global ocean to cool it down again, if only. So what this pipe represents is the heat content, the sort of fluid in this pipe is the heat content of the deep oceans, and therefore the level of water in the pipe is proportional to the sort of average deep ocean temperature. Okay? And this pipe is fatter than this one because the oceans have a bigger heat capacity than the atmosphere. So it takes more fluid, more energy to push up the temperatures of the oceans than it takes to push up the temperature of the atmosphere. Just to start with, to make things really simple, let's imagine the ocean, that this pipe is absolutely enormous. Okay? So just to sort of imagine first, the oceans are infinitely big. Okay? So I've just opened this tap, it's sort of trickling out here. So now the level in there can't change because I've just opened the tap at the bottom. If I now do what I did before, so I'll switch it back on again. Okay. And wait till it's back in equilibrium. Okay. So it's now back in equilibrium. Okay. Now I'm going to increase increase my greenhouse gas concentrations in the atmosphere, increase the rate of turning of the pump by the same amount that I did the first time before. Okay? By the same speed increase of the pump. Does anybody want to suggest what is now going to happen this time to the level of water, to the level of fluid in the atmosphere pipe compared to what happened the last time? Remember the last time it went up to about here the first time I did it? What do you think is going to happen this time? Do you see? Water is flowing out through here into the ocean and through here back out into space. So there's two outlets now, whereas before there was one. So just to sort of get you thinking, what do you think's going to happen? So before, when I increased the pump speed, it came up to about here. What do you think's going to happen this time? Yeah, it'll come up a bit lower. Let's do the experiment. Okay. And it's warmed up, but not as much. Okay? About half what it would do if it actually was allowed to, if it was actually just the tropical Pacific, just isolated from the oceans. And if I do it again, I can see that, again, if I increase it to that faster rate that I had before, again, it goes up again, but again by about half what it did before. So in the early stages of global warming, where energy is being carried off into the ocean as well as energy going back out into space, you see much less of the warming you eventually see when the system comes back into equilibrium. And this is really important because it means that if we were to keep our concentrations of greenhouse gases in the atmosphere constant at today's level forever, we wouldn't just see the warming we've already seen, it would keep warming. And this is why it's really important to understand this process, which is what we're focusing on in these lectures. So there's, in equations, that's the Earth's climate system, exactly the same principle. That's the extra energy flowing in due to the increase in greenhouse gases. And then there's this important parameter, which is the efficiency with which the Earth gets rid of energy to space. That's the plastic tube with an open outlet pipe. That was the first one we had. And here's the new one where we've got two outlet pipes, okay? And you'll see that because there's two of these Ks, you need less H for the same F, okay? Because this is a bigger number now. And we can sort of do exactly the same thing with the climate system because we've got this extra term, energy being transported down into the ocean. We see less heating for the same amount of increase in greenhouse gas concentrations. it's also really important to use this. You can understand it's a model not just of the total amount of increase in height, in depth of the ocean, but it's a good model of how it responds to changes in the incoming flow. So if I change the incoming flow down again, that means delta F, the change in F was negative, so my delta H is negative. It falls, and it falls quickly. Okay? I bump it up again, so it's a good model of how a change in flow affects a change in height. So we can go further than this. Same goes for temperature. It's a great model of how a change in greenhouse gases on short timescales causes a change in temperature. But now we've got to do something, make it a little bit more interesting, because the oceans are not infinite. We know that the energy's got to go somewhere. It's going down into the deep oceans and causing them to warm up. And that's represented by the increase in the level of the fluid over here. But let's start off here now. We're just taking this back down to its sort of, quotes, pre-industrial level, okay? So here we are, it's back in equilibrium. Okay, it's down at the this is the natural flow of energy into the climate system. And now, do you see the fluid is flowing back out into space? It can flow between these two pipes, but right now, because the level's about the same between them, it's not flowing. Yep, because it's balancing on both sides. So now this is the hard part. What's going to happen now if I crank up the speed of the pump? Someone go for it. It rises initially, and it rises initially just as much as it did before, and then with the ocean, with the infinite ocean, yeah. So it'll rise, and we'll do it in a minute, but I want you to think about it before we do it, because afterwards, one of the things in science is everything's always bleeding obvious when you've done it. Yeah, you never find a scientist who'll admit that they never didn't understand something at some point in the past. Because it's always like, oh yeah, it's always like net zero. Everybody thinks net zero is totally obvious. It's like 15 years ago, it wasn't obvious. I have to keep reminding myself this. Anyway, so do think about what will happen. It'll jump up to here, but then what's going to happen to the fluid in this pipe? It's going to start rising. It's going to rise slower because it's a fatter pipe. And what's then going to happen to the fluid in this pipe? Should we just do it and see what happens? Okay, I'll go for the slightly bigger acceleration. So you can see it immediately pushes up. This is the faster speed. Immediately it goes up, and then it seems to stop rising. But what's happening now? Watch it carefully compared to the ticks behind it. So this is constant concentrations of greenhouse gases in the atmosphere. Remember the wording of the Rio Convention. We're going to stabilize atmospheric concentrations of greenhouse gases at a level that will prevent dangerous anthropogenic interference in the climate system. Those were the words of the Rio Convention in 1992. So the level of greenhouse gases in the atmosphere is constant. The pump is set at a constant rate. What's happening to this surface temperature? Somebody who's close. It's still rising. Yeah? It's rising very slowly, and it's very hard to predict when that rise is going to stop. Because in order to know that, you need to know everything that's going on in the deep oceans. And as I emphasized, it's quite hard to see everything that's going on in the deep oceans. So let's take this back down to 0 again, and cool off our deep oceans so we can do some more experiments with it. Here we are, back down to where we started. So that's our right. So that's our new system. Now with the ocean in, let's think about in a little bit more detail of what actually happens when we crank up the speed of the pump. So I'll switch it up to by a factor of I'll increase the pump speed by sort of 1 unit. That was the first one we did. And this is what happens. You see, this goes up by that much, and then this is going up at a certain speed. And so it's pushing this up at a certain slow speed as well. If I do it again, it jumps up by the same amount again, and the speed with which this is going up also goes up by the same amount again. Now, you'll probably be relieved to hear we're going to go back to some maths. The whole point of this is to make you feel relieved to see some more maths. Here we are. So the change in depth that we see in a short time interval, a few seconds in that system, is proportional to two things. One thing that we know all about, which is the change in fluid flow. That would be the same even if the deep ocean wasn't there, or even if the deep ocean was infinitely large. Okay? So that's that first term. But there's another term, which is a rate of increase that depends on how fast the pump is turning. If the pump's turning quickly, it rises quickly. If the pump's turning slowly, it rises at a slower rate. So you've got one term which depends on the change in fluid input flow over that time interval, and another term that depends on the average fluid flow over that time interval. And now what's really interesting is, you can reorganize this, by the way. This is exactly the same equation, just I've replaced this. There's two constants here, but I can replace them with one constant that represents the sort of responsiveness to the flow. That's this kappa thing here. And then this other one which represents the rate at which it adjusts to a constant flow. That was the gradual rate at which it carried on adjusting after I made the flow constant. And this is where it gets interesting. We can do exactly the same thing for the global temperature. The change in global temperature over a multi-decade time interval is proportional to one term, which is just the change in greenhouse gas concentrations over that time interval, and another term that's the average greenhouse gas concentrations over that time interval multiplied by the length of the time interval. So you think, well, okay, that seemed like a lot of work. Where does this get us? Well, what would it take? So first of all, it tells you that, I've already mentioned this, that Article 2 of the Rio Convention, which was stabilizing greenhouse gas concentrations at a level, is a sort of problematic target to have because the world will just continue to warm for a very long time, many centuries, if that's all we do. But the other really interesting thing it tells you is, actually, well, wait a minute, before we get on to that, I could just ask you how well this very simple equation, so I've got this very simple equation here. Here you are. It may not look that simple, but compared to a climate model, this is pretty simple. So it's just got two terms in it. The change in the energy flow at the top of the atmosphere, the energy imbalance at the top of the atmosphere, and the average energy imbalance at the top of the atmosphere, okay? Just adding those two things up and comparing that to these dots, which are the output of the most advanced climate models in the world. And you can see, they wobble around because of variations in the climate, variable weather and so on, but broadly speaking, we can understand it. Here's the Met Office model, which, by the way, you'll notice that, by the way, you'll say, well, there's still some, if you're picky, you'd say, well, there's a bit of a discrepancy there. But hang on, look at the models which we're comparing against. And, the Met Office model actually shows no warming at all up until the present, and then it takes off like a rocket. So, the discrepancies between this very simple equation and these very advanced models are smaller than the differences between the models themselves. I should, of course, stress, because there is somebody from Bayes in the room, that there's many more uses, and we don't want to replace the Met Office with a bunch of plastic pipes. There's many more uses for climate models than just predicting global temperature. But the point is you can understand what the climate models tell you about global temperature, without believing every detail of what the climate model is simulating. And that's really important because people find these climate models quite bewildering. They're sort of black boxes. There's lots of ways in which they can go wrong. There's lots of things you can nitpick over in them. But it's important that the fundamental physics of what drives changes in global temperature is actually very simple. We can capture it with just this simple equation. Now comes the punchline. Bang on time. What will it take to stop global warming? Okay? So you want delta T, the change in temperature over a multi-decade time interval, to be what if you stopped global warming? Answer is obvious, 0, okay? So you want delta T to be 0. This is an equation, so we've got to get this side to be 0 as well. And there's two ways to do that. One way is to make everything in here 0, yeah? Because 0 plus 0 is 0. The only way we could do that is to make the average energy flow due to extra greenhouse gases 0. That means getting greenhouse gas concentrations back to pre-industrial. That would be hard. Maybe one day, in many thousands of years' time, we may get that. But there's another way to make this 0. What's that? There's two terms here, and I want them to add up to 0. One of them has to be negative, okay? Now, this average term, that's the average energy imbalance due to past increases in greenhouse gases. We're kind of stuck with that being positive, yeah? Because greenhouse gases have gone up, and they're not going down again anytime soon. But that could be negative. Do you want to say how much it has to be negative? Well, in order to get it, it's this number is crucial, yeah? If the ratio between delta F and F bar delta T, or between the change in flow and the average flow multiplied by the length of the time interval, is this rate, then this will average to 0. In fact, that's down here. Sorry, I was covering it up. So if delta F on delta, hopefully you can see that, just rearranging this equation. If delta F on delta T, which is the sort of rate of change of the fluid flow, divided by the average rate of the fluid flow, is equal to negative this rate, so-called the rate of adjustment to constant forcing, which is about 0.3% per year, 3% per decade, then we get no further warming. So let's try this experiment. This is a simulation where I'm going to increase the flow over 10 seconds or so, and then I'm going to gently decrease it. I want you to watch and see what happens. After a couple of seconds, okay, you can see it's starting to go up. Over 10 seconds, it's accelerating. Greenhouse gas concentrations are rising in the atmosphere, okay? And temperature goes up. And now it's stopped increasing. And if you listen carefully, you can hear that it's slowly slowing down again. Yeah? Yeah? And what's now happening to the level of fluid in this pipe? I'm hoping it's not moving. Yeah? Because that's the point. Even though the ocean is still warming up and the rate of the pump is going down, that corresponds to greenhouse gas concentrations coming down in the atmosphere, these two effects balance each other and we get no further warming. That's what we mean by net zero. It doesn't mean we've got constant concentrations of greenhouse gases in the atmosphere. It's now switched itself off again. It doesn't mean we've got constant concentrations of greenhouse gases in the atmosphere. It means we're reducing the concentration fast enough to balance this accumulation of heat in the deep oceans. And how we get concentrations falling at that rate is, of course, the subject of our carbon cycle lecture, which will be coming up in a couple of lectures' time. So there you are. This is, if you like, a good enough model for climate policy. Changes in temperature over decade to century timescales are just how much do you change the concentrations of greenhouse gases over that period, plus what level are they at. For fast changes, this dominates. For slow changes, as you're approaching equilibrium, this becomes important as well. And if you want to know what it takes to get delta T to zero, you have to get these two to balance, which means you have to have declining concentrations of greenhouse gases in the atmosphere. And by the way, for the enthusiasts, here's the gory details of the whole set of equations that runs this, and I'm not going to go through all of that. And for those of you here, this is the sort of stuff you'll do when you're doing. Actually, you probably won't even do coupled differential equations in further maths. You might do. I'm not quite sure. I can't quite remember. And this term is that additional energy flow to the deep ocean due to the fact that the system's out of equilibrium. And by the way, if you think about it, this exact same set of equations is the set of equations that governs the fluid in these pipes. So it's a nice example of how you can do coupled differential equations with fluid in pipes. Finally, there's one more term, which is just an important one, which I sort of add for completeness. This is here. It's the additional energy flow to space that results from the system being out of equilibrium. For this model to be truly realistic, the length of this pipe would have to somehow adjust to the pressure difference between these two tubes. And we couldn't work out how to do that. Okay, so, but if you can maths to the rescue, you can actually rearrange this and discover that it satisfies the same equations anyway. That's left as an exercise. And by the way, if you're really interested in this, indomitable nerds can go and read a paper free online, Net Zero Science, Origins and Implications, which has all the maths in it. Although I have been told by a colleague that the maths is somewhat gratuitous and it's perfectly possible to follow the paper without the maths. He was sort of slightly teasing me about the fact that I put all these equations in there. He felt rather unnecessarily. Anyway, that's the slow adjustment term because as the world warms and heads back to equilibrium, the pattern of warming changes, which changes the efficiency with which the planet sheds energy back into space. This is a really important term. Sorry, I should remember to switch this off. Now that it's done its thing. This is a really important term because it adds to the considerable level of uncertainty we have in where the warming will stop if we were to hold concentrations of greenhouse gases at today's level forever. But fortunately, there's another option. If we can get greenhouse gas concentrations falling fast enough, we never need to worry about all this. And that's really important. So, the ocean physics behind net zero. First of all, how the circulation of the oceans keeps the deep ocean cold. So the deep ocean it's not sort of cold by accident, it's kept cold by the fact that all of the water down in the deep oceans comes from the Arctic. And this slow, we call it the thermohaline circulation, provides that multi-century timescale response that's represented in our little model by the fat pipe over on the right. And just thinking about these two this sort of simple pipe model, you can realize that just two quantities, the so-called transient climate response to forcing, that's how much it jumps up when I crank up the speed of the pump, and the rate of adjustment to constant forcing, that's the rate at which it continues to rise when I stop changing the speed of the pump, are enough to understand global temperature changes on decade to century timescales and to understand what it takes to stop global warming. Thank you.
Thank you so much, Professor Allen. I've got a couple of questions online before we go to the room, if that's all right. The first one is, does the temperature of the Earth's core have any influence on deep ocean temperature, i.e., e.g., rather like the way temperature rises in a deep mine?
Great question. There's a very gentle trickle of energy into the bottom of the ocean from geothermal heat in mid-ocean ridges, columns of boiling water coming out of mid-ocean ridges. You've probably seen movies of that. But compared to the volume of the ocean itself, it's tiny. If the ocean circulation wasn't happening, it would eventually warm the oceans up. So you've got to be careful with numbers like tiny, because you've got to think, well, in what context? Over billions of years, that would warm the oceans up. But the oceans are kept cold by that ocean circulation anyway.
Second question I've got from online is, this makes it all seem quite simple. Is it really that simple? And does everyone agree that it is simple?
If you want to understand global temperature, then it pretty much is that simple, at least so far. Important proviso there. So far, the response of global temperature to global changes in greenhouse gas concentrations has been remarkably simple. And by the way, this again wasn't obvious. I remember when I started in this field, when I was doing my doctorate back in the sort of late 1980s, early 1990s, I remember going to lectures where, people were saying, the university I was at, or the university I'm still at actually, people were saying, we understand chaos, we understand that things are very complicated, and it's only these sort of naive geographers who think that when you ramp up the greenhouse gases, it'll be very simple and it'll follow. Anyway, turns out on that score, the geographers were quite right. Basically, you crank up greenhouse gases, world warmed up in a very predictable way. So far, we shall see what happens in the future.
I have one more question from online before turning to the room, if you'll forgive me. The deep sea is kept cold by the Arctic. Does the Antarctic play a role at all?
Sorry, yes, I should have emphasized Arctic regions. We tend to use the phrase to refer to both. Deep water is formed around Antarctica and also in the North Atlantic. So both regions play an important role.
Thank you. You've talked about politicians' obsession with stabilizing greenhouse emissions and the difficulty of explaining climate science to politicians. Is that just another tragic feature of the two cultures, that politicians learn humanities and journalists and don't understand basic scientific concepts?
To be fair, the political community got on board net zero remarkably quickly. We did this work. We established that it wasn't enough to stabilize concentrations. You actually had to get concentrations going down. That work was done in the late 2000s, and the Paris Agreement, which essentially acknowledges that and moves on from that stabilization framing of Rio, was signed in 2015. So, yes, it's a perpetual struggle communicating, but it can work. And on that occasion, I think the politicians did take this on quite quickly. That said, we have to sort of keep reminding people of this because, as we'll come on to in the carbon cycle lecture, there's an increasing tendency these days for countries and companies and so on to sort of declare they've got to net zero when they're no longer, when there's sort of balance in the atmosphere, when effectively their activities would stabilize greenhouse gas concentrations in the atmosphere. And you have to remind them, no, that's not what we meant by net zero. You need to go beyond that. I'll explain more about that in the carbon cycle lecture. But it's still topical, therefore.
I understand that temperatures in Kodiak Island in Alaska in 1st of January 2021 reached 19 degrees C. The Antarctic has been apparently recorded as having temperatures at 30 degrees above average. How is this affecting deep water, cold water formation and the haline circulation?
Yes, yeah, so... So obviously the changes in the temperature in these regions are particularly important because the ocean will be remembering those changes for hundreds of years. If you warm up in a given year, if you warm up the Labrador Sea, then the water that enters the deep ocean from the Labrador Sea will remember that temperature for centuries. So these changes really matter, even if they only happen in a given season. The Earth will remember them for a long time. So, and they're not, they're happening more and more often. So exactly, it's building up. So it's very important. This, of course, is why we need complicated climate models as well as fluid in pipes in order to understand how those changes in these regions actually affect the penetration of heat into the ocean depths. And of course, a big worry and a point that I will look at later in these lectures, or we may have to delve into it more later on in the because it involves even more maths, is the danger that if you mess with the system enough, then you could actually affect the ocean circulation itself. And for example, if you were to shut down the entire ocean circulation, you'd have a huge impact on climate, which would be very difficult to reverse. That's not predicted to happen anytime soon, but as I say, just because it doesn't happen in models doesn't mean it can't happen in the real world. It's certainly a worry and one which we're watching, and one of the reasons why people are particularly concerned about these huge changes we're seeing in Arctic regions is because we know not only are they a very sort of sensitive indicator region, but they play an absolutely vital role in what controls our global climate. So the fact that every litre of water in the Earth's oceans over the vast bulk of the depth has probably got there via the Arctic tells you just how important changes in the Arctic or Antarctica, tells you just how important for future climate changes today in the Arctic and Antarctica are.
Thank you so much, Professor Allen. Professor Allen's next lecture is going to be on the 7th of March.
Yes, and in view of the fact that, so in a slight shift to the programme, earlier, we were going to sort of work through the science and then come back to the policy in the final lecture. But because we've got an energy bill in front of Parliament at the moment, and also because I felt, having got through this lecture, that you might want to break from the algebra and get back to politics, we'll talk about what the UK is trying to do to get to net zero and what we could put into the energy bill to make it happen in the next lecture. So we'll sort of get stuck into some of the policy implications of the need for net zero next time. And then but don't worry, the plastic pipes will make a reappearance in the last two lectures when we get on to understanding the carbon cycle and what it'll take to get atmospheric concentrations of greenhouse gases going down fast enough to stop global warming. So see you on the 7th of March.
Thank you so much, Professor Allen.